Messieurs, dames, bonjour. We present research work, verification of cryptocurrency consensus protocol, reinterval correlate Petronet model design. I would like to introduce the international research team, which includes Dmitry Zaitsev and Shmilova Tatiana from University Côte d'Azur, Nice, France, Ding Liu and Zhou Zhou from Xi'an University. Our international team has deep roots of cooperation, which started in 2011 with China-Ukraine joint project Manufacture Control Desert, Petronets. Recently, we moved to University Côte d'Azur and represent the laboratory I3AZ. School of Electromechanical Engineering of Xi'an University has deep roots in application of Petronets for manufacturing process. So here is the site of laboratory I3AZ, and you can also see the site of Xi'an University. Recently, Dmitry Zaitsev visited Xi'an University this summer for international summer course program, where during the close cooperation with master students, the final model has been refined. We apply CPN2's modeling system for modeling networks, protocols, and software. CPN2 represents a combination of Petronet graph, very popular for modeling of concurrent systems, with a functional programming language ML. This union of graphical tools with a functional programming language is very powerful. It uses also hierarchical model design with a transition substitution and represents timing characteristics. Recently, functional programming languages are very popular, especially with respect to formal verification of software. As for our tools, we use CPN tools, which you can freely download from its website. Now we apply upgraded version of modeling system, CPN IDE. We have more than 20 years experience of models constructing in colored Petronets form. They are absorbed in verification of protocols and performance evaluation of networks. It is very significant for cryptocurrencies to be correct and to be efficient, because it conserves rather big funds. As for our experience of modeling and simulation, you can download our models from the official site of CPN Tools, as well from GitHub repositories of Dmitry Zaitsev and Tatiana Shmilova. Each model in this repository has references to paper or book, so there is complete description of models and obtained results. And as additional literature, we recommended our textbook, which you can download freely from the website of Dmitry Zaitsev. This textbook is the one of most cited our papers in Google Scholar.
Recent decade, we observed the process of cryptocurrency development. Let us consider in detail characteristic of this phenomenon of cryptocurrency. At first, it is peer-to-peer distributed system of anonymous nodes. Transactions are aggregated into blocks, and node keeps a copy of ledger, each node, chain of blocks, or blockchain. Node is identified as a pair of crypto keys, one open and one private, and to make decisions, nodes use consensus protocols. Bitcoin represents the first cryptocurrency and the most widespread in the world. It uses proof of work kind of acknowledgement of seriousness of intention of nodes. it spends a good deal of computer resources to resolve some puzzle to acknowledge seriousness of intentions. The number of nodes of Bitcoin is about 16,000. The total amount is about 20 millions of coins, each of 29,000 euro. The number of blocks 800,000, and the block time approximately 10 minutes. The second cryptocurrency is Ethereum, and the proof of stake protocol, which is based on the validators who staked their own money, is kind of green protocol because it is not wasting resources of our computers. The number of nodes is approximately 10,000, and we have total amount of the cryptocurrency like 120 million coins, each coin $1,800. The total number of blocks is about 18 million, and block time is rather short, about 20 seconds, minimum 12 seconds. We can open sites of Bitcoin and Ethereum and find plenty of useful information. Also, we can observe distribution of nodes all around the world, and the similar scheme I'm using as background for this presentation. Cryptocurrency comparison is represented in the following table. Here we have more cryptocurrencies, including Dash, but uses rather interesting scheme of 11 hashing algorithms, and Ripple, which is using special kind of federated consensus protocol to come to the consensus. And as for hashing, cryptocurrencies use this approach to check integrity when big data is analyzed by an algorithm, and a fixed amount of numbers is computed to check the corresponding integrity. More sophisticated schemes of multi-level hashing, including Merkle trees and Merkle trees, are applied within cryptocurrencies. Here we are interested in consensus protocols because we model them. They represent decision, collective decision of this distributed system. So they broadcast messages, and they should be stable either to attacks on networks or to malicious behavior of nodes, which is traditionally called Byzantine node tolerance. So there could be random behavior of Byzantine nodes, as well as conspiracy of groups of nodes. We studied consensus protocol that was initially offered in Keller and Bemer paper and refined in our previous paper, where we developed conventional model of consensus protocol. The main part of protocol is based on activation messages generated periodically by environment that corresponds to resolving by a node of puzzle. Node increments its preferred value and propagates it using broadcasting messages to other nodes, which increment vote for the corresponding value and replace node's preferred value. Finally, a consensus value is formed and a decision is made, and activation messages are periodical. They have some random node choice implemented and exponentially distributed time between activations. We've implemented this protocol using conventional model, and now we are glad to present its reenterable model, which is well scalable and can manage real-life scale of this distributed system, counting dozens of thousands of nodes.
Verification of protocols and software is a very significant topic. Verification represents an asset security proof. In the view of high price of errors or imperfection, it is highly recommended for cryptocurrencies. We can apply formal methods and simulation techniques. Formal methods application requires simplification of domain, while simulation works with a detailed model. We use colored PetriNet as a both model checking technique and the simulation language. Reenterable models allow us to manage big data. We published a conventional CPN model of consensus protocol a year ago with our colleagues from Johann Kepler University, supported by Zsesz grant of Austria Academy of Science. Conventional model is rather good and vivid for educational purposes, but it is difficult to scale it. Conventional model is created by the direct mapping of networks. That it is easy to understand such model and train messages. From each new node should be drawn or copied separately. Here we see 11 nodes attached to place media that represent network and the subnet environment that represents proof of work specific item. Rentable model composition principles are the following. Develop rentable components. Add a single copy of each component. Provide connection of components that allows actual connection in any valid topology. An additional compact description of the network topology. The next, supply dynamic elements of model with a topology. And provide switching of topological text that models the movement of dynamic elements. Rentable models contains each component in one copy. To scale the model, for instance, increasing the number of attached nodes, we need to correct a single constant value. These components are more sophisticated, providing rentability and switching of text. Here, the topological type is represented by the node number.
I'm Zoe Zhou. I'm going to talk about harm between conventional model and reenterable model. This figure represents a comparison with the conventional model, which curve comes out of the grid range at about 300 nodes with the simulation time about 6 times greater than the simulation time of reenterable model. Now I'm going to talk about how to create hundreds of nodes in the conventional model. This is a conventional model with 10 nodes. To build a model with hundreds of nodes, we can use republication method to replicate 10 nodes at once. For an example, I only replicate one node this time. The first step is to build a new group and then toggle one node. The last step is clone this node. And then change this node's length. Now we can clone an arc and link this new node to the media. But we can see it is not assigned. So we need to assign it to the socket. Now a new node has been created. So we need to change this value to 12. The model has been created. We only need to wait for the computer to construct it. As for the actual libraries of the model composition process on the specified laptop, about 40 hours were required to compose the model having 300 nodes, and during 14 more hours, the modeling system was processing it before the simulation. Thus, application of the rangeable model for real-life scale simulation is cut of must.
Let us consider design of reenterable model. As for the modeling by CPN tools, I recommend you my tutorial for Africon 2021 conference. So the model contains 3 levels of hierarchy. The basic main page of model uses 2 components, environment and node. And node uses, according to the protocol, 3 event handlers: init, activation, and deliver, and additional monitor that checks termination condition. Now we switch to the CPN tools modeling system, and we can check hierarchy using the main page of model. For instance, I point to hierarchy tag and use show page to find out how environment page looks like. I return to the main page and look, for instance, node, and I have a picture of node subpage. And in the same way, I can come to the 3rd level of hierarchy, opening the corresponding transitions of Petri nets, which are substituted by some subnets. As for the main window of the modeling system, to the left we have index. Here in the index we have tools. For instance, create tool. If we move it here, we have its graphical representation for creation polyt of instrument to draw net. We have here the name of the file for our model, declarations of constants, so-called values, color sets, variables, and function. If we close declarations, we can see pages of models what represents hierarchy using offsets for these models. Now we have 100 nodes, and we can observe the corresponding text in this multiset. I will use smaller number of nodes to have fast simulation. I introduce a small value, 20, maybe 21 nodes to have an odd number. The model is rechecked when it is black. There is no aura. After some amount of time, we can start simulation, and here we have a button for automatic simulation. Now I start it, and we observe the result. Here consensus is achieved. Though we have 1/2 of Byzantine nodes, I repeat the simulation a few times, and finally we will come to some value when we have result of simulation, but represent. I emitted a series of simulations, and now we consider how consent or consensus looks like. So here we have two words, 1 and 2. We have the corresponding groups of nodes, and we can calculate how many representatives, how many nodes voted for each of two values. In this example, we have component activation, and when we send broadcasting message, delivery message, here we have definite part of nodes which have Byzantine behavior represented as random preferred value. In our case, we have 1/2 of Byzantine nodes, and for the majority of runs for our simulations, we have absence of consensus. I remind you that here we have two values like yes or no, two votes, but we can change this constant easily and have bigger number of votes. Let us consider environment. Environment component now contains feedback of modeling system. We have definite times when our model stopped. So here for debugging purposes, we have a trace of each message together with time when it was sent to the network. Component node contains specification of event handlers. We can check votes for each node, for each value, so we can find out how they came to consensus. And here there is init component to initiate values of node, preferred value, and initial values for each magnitude for which it is possible to provide votes. We have activation node, which function is increment preferred value and start broadcasting. And we have deliver, the event handler that processes deliver message. Deliver message processing changes number of votes for the transmitted value and compares it. If the number of votes increases the number of votes for the preferred value of this node, they are swapped. Current preferred value is replaced by the value transmitted within the message. Terminate condition is the simple monitor that checks that the number of votes exceed the threshold k, even as a constant. So it terminates work of node because it takes the node number from the total list of nodes, and node stops working after termination condition was achieved. You can see that reenterable model allows us to implement fast simulation and made our model scalable. So we return to the initial state, for instance, change number of nodes to 101, for instance, and after a while, when our model becomes black, it means it passed the syntax check. It is ready for simulations, and I can start simulation and wait when it will be completed. So I need to come to initial state and start simulation. We could wait or not when it will be completed, but I believe now you are familiar with colored PetriNet model design and basics of work with CPN tools. As for the tutorial, I recommend you tutorial for IEEE African conference, where during 4 hours, with help of my best students from environmental university situated in Odessa, Ukraine, we described basics of work with CPN tools and models design.
I'm Dr. Ding Liu. Let me follow up the rest of the slides. This figure is a comparison of re-enterable and conventional model simulation results. The number of activations before consensus depending on the network maximum delay. This figure shows results for the time required to achieve consensus when we use exponential distribution with parameter 10.0 for activation delays and uniform distribution with specified on the graph maximum value for the broadcasting message delivery time. Values greater than 4,000 lead to the absence of consensus in more than 95% of runs. From the graph, we can see that two curves come rather close to each other. And next, in this figure, we show how many activation messages are required to reach a consensus depending on the fraction of Byzantine nodes. With the increase of Byzantine nodes, number of activations before consensus will also increase. The construction of earlier designed models is based on the direct mapping of the network structural scheme. This work compares the re-enterable colored PetriNet model with an earlier designed model. The comparison proves the fact that functioning of the models is a kind of isomorphic, with basic characteristics equal in bounds of some negligible statistical error of 2 to 3%. Thus, we can use re-enterable models instead of conventional models. That considerably decreases the laboriousness of handling big models and simulation time required for full extent comprehensive investigations of the cryptocurrency protocols and software for both verification and efficiency optimization purposes. That concludes our work. This work was supported by both French and Chinese grants. We appreciate all efforts and helps from our colleagues of both sides. Thank you. And if you have any questions, you are welcome to contact the team. Thank you.